Okay, well, just let me, okay, there's a question about regex. I have to just review a little bit here. The problems on dimensions, and we have asked the questions, what's the dimension of M53? So if what is M53 is a vector space, is the vector space of all these matrices where I've got like all the 15 variables here. And here's a basis where I have a 1 in each slot for each variable. And so this forms a right M as a span, and these vectors are all linearly independent because I can't play one of them off against another because the X appears here, but everywhere else there's a 0. So you can sort of see that dimension of M53 is going to be 5 times 3, the number of components, which is 15. The dimension of MRS is R times S. And now we're looking at the dimension of P to the N, the space of order n polynomials. And first we start off with P1. And we can see here that P1 equals the span of 1x, right? It's just, now these vectors are linear. I can't write a number times x and get 1. I can't get rid of the x in any way. So this is, so the dimension of P1 equals 2. Now let's look at P2. P2 equals A times 1 plus B times X plus C times X squared, where A, B, and C are members of R. Well, that's literally equals the span, that's the set of all linear combinations of 1x, x squared. So this is a basis for P1. This is going to be a basis for P2 because they span the space to linearly independent. So the dimension of P2 equals 3. And you can see that you can see by the similar that P3 is going to have a basis of 1x, x squared, x cubed, and a dimension of P3 equals 4. The reason is because it's sort of like you're starting from 0, 0, 1, 2, 3. So you're labeling it by the highest order polynomial, but the dimension is one more than that. So in general, the dimension of P to the N is going to equal N plus 1. So that's P to the N. And then this last vector space here, well, the question here is, we've written as a span. So the only question is, are these vectors linearly independent, right? And so what you need to do for this one is take this, formally it's going to be a 4 by 1, 2, 3, 4, a 4 by 5 matrix, and do row operations to reduce it to echelon form. And unless you can, eyeball it in some sense that there's some, well, we know that one thing is, let's say I wrote down here this matrix. The matrix from here is going to be 1, 2, 3, 4, 5, 1, 5, 5, 4, 1, 4, 4, 4, 1, 4, minus 2, 1, 2, 1, 1. Well, this is a 4 by 5 matrix, right? Yeah. Well, you know that the maximum row rank is 4, right? So you know that the column space has got to have a dependent vector, right? Because the column rank has to be the same. So the dimension of the columns has to be 4 too. So that means the rank of the matrix is going to be less than, it's going to be 4 at most. So this set's definitely dependent, right? So, but there's an answer to the question of what's the dimension. It's so the problem then is, well, how do I find the dimension? Well, what I would have to do is apply, say, with this linear combination equals 0, right? So what I'd have to do is solve the linear system here, 0, 0, 0, 0, and ask if it has, or the point, or the simplest one is to find the dimension, maybe, is to just do row operations on this matrix and bring it to echelon form. And if I bring it to echelon form, then it's going to be the number of non-zero rows will be the rank, and that will be the dimension of this space, right? Because the dimension of the space is the column rank of this matrix, which is the same as the row rank. So I can just put this into echelon form, and the number of non-zero rows will be the dimension of this space. Okay, so the logic is you form the matrix here, and note that this then is the column space of this matrix. The column rank of this matrix equals the row rank. The row rank equals the number of non-zero rows in echelon form. So I just would have to take this and do lots of row operations, maybe minus row 2 plus row 1.
I think reducing this is quite a few steps.
Yes, it's quite a few steps, and helpful because you do minus row 2 plus row 3 and minus row 2 plus row 4.
All the work, I did this probably a few years ago, so I have the reduced echelon form if you want.
Okay, but so what did you get?
So it was,
I mean, the question is how many non-zero rows?
I got 2.
Two.
I'm sorry, 3 non-zero rows.
3 non-zero rows. So that means the rank would equal 3, right? So the dimension of the space would be 3. And then we could check, right? Isn't there, oh, doesn't it? Oh, this isn't due yet, right?
No, I think it's due tomorrow.
Right, but that means I can't just check. There's no show answer here yet. Okay, so that's how you would do it. That's how you would solve the problem. I don't think there's any royal road to solving this problem otherwise. So it's a little bit misleading problem in the sense that these are just sort of relatively straightforward, but this one is a little complicated. Okay, so does that any other questions that you thought of? So we have 4. Let's see. Oh, let's ask. Oh, yes. Okay, so let's ask. What is the representation of we see 1, 1, 1 in the basis 1, 0, 0, 1, 1, 0. Here's the basis B of R3C 1, 1, 1. So I'm telling you that this is a basis, right? Okay, so here's a basis, and here's my vector V. So this is the standard basis. What is the representation of this vector in basis B? Do you guys have an idea? Or not? Well, let me go ahead and.
Well, R through C is already in the basis.
Well, this is in the standard basis, right? We want to know what is it in this basis. We want to represent this vector in this basis. So when you're given a vector like this, V is given in standard basis. It's a little bit confusing because these basis vectors are also given in the standard basis, but we're sort of asking, what if I want to translate everything to this other basis? Okay, so what I want to do is, well, if this vector is in R3C, and this is a basis of R3C, I should be able to write 1, 1, 1 equals some number times the first vector, plus some number times the second vector, plus some number times the third vector. And since it's a basis, there's a unique set of numbers, A, B, and C, for which this is true. So, can you see a solution? Yes?
Well, you could turn it into a matrix and then solve it.
That's true, you could. But I want you to look at this and see if you see anything interesting about these vectors.
I mean, it's almost an identity matrix.
Well, what I mean is, do you see 1, 1, 1? You see 1, 1, 1 is the vector, but do you see it on the right also? So how could you choose A, B, and C so this is true?
Well, we have it C equal 1.
C is equal to 1.
Yeah.
Then what would these be?
0.
0. So I could just put in 0, 0, 1 here. I could go through and solve it. I mean, you may not see that, but that's always a good thing to check. Is this vector one of the basis vectors, right? Okay, well, what does that mean for the representation of this vector in basis B? Well, it equals 0, 0, 1 in basis B. Okay, so it's a little bit disconcerting, right? To make it clear, we could put this little e here for the symbol for standard basis if you wanted. Just so it didn't seem so. See, you're used to thinking of the vectors just these components, right? But here, 1, 1, 1 equals 1, 1, 1 in the standard basis equals 0, 0, 1 in basis B, right? Okay, so let's maybe go and maybe we can try another simpler. Let's try what is the vector 1, 2 in basis B equals 1, 1, 1 minus 1. So here's a vector V. We want to know what vector V is in basis B. So, do you see how to start? Well, the first question is to set this up. This will involve potentially making it. So, well, I can start it for you just so you can get going. But what you do is you put 1, 2, and right is a linear combination of these. So I'm going to write them. It's easier to write them. Normally you'd write on the right, but we could write it this way. We have to have that A times 1, 1 plus B times 1 minus 1 equals 1, 2. Well, there's the vector form of equation. And what we want to do then is we can write this is the vector form of a linear system. We can write the augmented matrix down for this linear system. Okay. The columns of these are like the column vectors. So this is saying, is this vector in the column space of this matrix, right? So we could just go ahead and, as you work on it, I'll work on it too. Okay, so there's the answer, right? Now, what does that actually mean? How can you show that's true? Well, this one is just 1, 1, right? But what this notation means is 3 halves times 1, 1 plus minus 1 half times 1 minus 1, and these should be equal, right? So this is going to be 3 halves plus minus 1 half um, 1 half, right? Now, did I get this right? Let me make sure, because it doesn't look right. So let me just check. Minus 0. B equals minus 1 half. Oh, 3. Yeah, 3 halves. Oh, yes. Because I'm wrong. The matrix, it wasn't 1, 1, it was 1, 2. That's why I misquoted the original starting point. That's why it didn't work. So we have 1, 2 is, I just wrote down the vector we start from is 1, 2. So that makes sense here, because then I multiply this in. This is going to give me 3 halves minus 1 half is 1, and 3 halves plus 1 half is 4 halves, which is 2. So it checks. Right? So this is sort of a notational thing, but it's like so you want to realize that the representation of a vector in one linear system can be rewritten in terms of a different basis. Okay, so I know that I'm using it all the time. I guess you don't mind if I do this. Okay. So let's see, make sure. Okay, good. Okay, so we can go to another example and say, let's do this. Let's find the representation of one. Okay. Find representation of 1 plus x in let's do 1 plus 2x in 1 in the basis 1 plus x, 1 minus x of P1. Okay? Find representation of V equals 1 plus 2x in the basis 1 plus x, 1 minus x. Okay, so what do we do? We do the same thing we do, so we write, this is a basis, so it has, so if this is in this, since this is a linear polynomial, it has to be in this basis, but this is sort of given in the standard basis, right? So we want to write this vector as a linear combination of these, a times 1 plus x plus b times 1 minus x, right? Now, this is the special equality which says the polynomials on the left or the right are the same polynomial. It's not a numerical equation, it's saying they're the same function, the same polynomial. So that means we have to equate them term by term, and the simplest way of doing that is in the standard, we sort of multiply them by coefficients. So here we have a plus b, we could write this out as a plus ax plus b minus bx, which equals a plus b plus a minus b times x, right? So that means the equations we have are a plus b has to equal 1, because the constant term has to equal. Then we have to have a minus b equals 2. Okay, well, we could make this into a vector equation, right? We could look at this as a plus b, a minus b equals 1, 2. And then we could divide this up into a times 1, 1 plus b times 1 minus 1 equals 1, 2. Right? But look, this is the same equation we had before. This was the equation we solved in the previous example, right? See, it was 1, 2, a times 1, 1 plus b times 1 minus 1. So we already know the answer. We already know that for this, that a equals 3/2 and b equals minus 1/2, and just by plugging in, you can see that, okay? So the representation, see, the point is, the representation is when I go here, the representation of, well, let's look at it this way. The representation of 1 plus 2x in the standard basis equals 1, 2. Okay? And so so 1 plus 2x equals 3/2 minus 1/2 in basis b, up here in b. So what this means is this equals, we can check that what this means, 3/2 times 1 plus x minus 1/2 times 1 minus x, which equals, well, that's 3/2 minus 1/2 is 1, plus 3/2 x plus 1/2 x is 2x. So it works. Another way we could ask is, let's say this is so that the answer to this question is what is the representation of this vector? Is this representation here? And the question is, what about this? Let's say I had the vector 3, 2 in basis b. What is that in the standard basis? What polynomial is that standard basis? Right? Well, I'd say, well, this is equal to 3 times 1 plus x plus 2 times 1 minus x, because that's what basis b is. It says the components here are the coefficients of the basis vectors. 1 plus x and 1 minus, that's what this notation means. So then we can write this as 3 plus 2 is 5 plus 3 minus 2 is 1 times x, so it's 5 plus x. So you can go back and forth between this is the vector, and we can say, well, this is equal to 5, 1 in the standard basis. So this is this, we're going to do more with these bases, you know. Okay, but let's, so what kind of problem do you want me to solve now? If you have a question, that would help you, we've sort of surveyed almost everything in this chapter in one way or the other. I mean, there's lots more problems we can do more on Thursday, but how about you guys? Do you have any problems you want me to solve? Even if they're really simple.
Oh, could we do proofs like potential proofs that could be on the demonstration or something?
Let's see. Well, let me see. Let me see what, well, let's go and look at, I've forgotten what is on the demonstration, but let's look and see what the titles of the problems are so that you have some sort of hints about what actually it looks like. So here is demonstration 2. Okay, matrix algebra, right? Matrix inverses, matrix equations, subsets, vectors and spans, linear independence, rank and independence, vectors and bases. So it doesn't, let's see, has a question on rank, vectors and bases. This is like the kind of problem we just did. So it does, so it covers, so it's not pretty clear what the, I think that where I would give, what for a demonstration, it would be like, or you're thinking maybe the point is one of the, if it was one, and I've forgotten if there is exactly, it would be of the following. It would be like something in here, right? So is there one of these problems that, oh no, vector space is down here. Let's see. The question is, like for example here, there's all these examples. The question is, this is it's like it'd probably be something that has to do with this is the linear independence test, right? You have your premise is you're supposing the linear combination of vectors implies this is a consequence. And then if I had a proof, it would be something like this where you were doing, I would give you justifications and go through. This is how you solve one of these problems, right? It would be, is this set linearly independent? So the answer to this question is the set linearly independent is like a proof-like thing. So if I had a proof, it would be something rather than some random extra proof like you've had on the assignments. It would be something like this where I give you these steps and ask you what the justifications were. So I guess then the question is, do you have any questions about these problems where you're unsure of what?
Not really. It's just knowing what each of the actions mean, right?
Excuse me?
It's just like you just need to know what the actions or justifications means, and then
yeah. So if you go through and review this and sort of understand what these answers are, what you should have here, then that's the kind of thing. And here you can see I've done. There's examples with 3 vectors. Here's one with polynomials. It's the same pattern. And here's one with matrix vectors, but it's the same pattern. So that's linear independence. And let's see if we go on to less more linear independence. Wait, did I get? Oh, these vectors span the space. This is a little bit different. This is sort of like saying for all vectors W, so that you, but it's the same thing in terms of justifications. And this is doing, yeah, so if there was some, if there's anything, it's going to be like one of these problems here.
Are we gonna have a Lix file? Like the last demonstration?
No mix file.
Huh?
There's no mix file.
Oh, okay.
So this is entirely regex questions. So it's sort of more like a concept check in that sense. There may be some linear, but it's a little bit more intense than a concept check, but it's not it's not going to require as much work as demonstration one.
Okay. I was just curious.
No, that's good. I mean, if you sort of have a sense, then you'll be less, you'll know sort of how to prepare for it better, so you won't be surprised. Hopefully.
And for the demonstration, they won't be due until the end of
So
break.
it won't be due until like say Tuesday night after the break.
Oh, okay.
Monday night after the break rather than two. Because after because I have other classes but no office hours on Monday, so it's like the 20th or 21st.
Okay.
So you can sort of decide whether it's better to start early, or if you wait, then you can study more, but then you might forget stuff. So who knows what, anyway.